Today we will talk about further regarding the Diels-Alder reaction, which falls under the category of cycloaddition reactions of pericyclic reactions. So this will be the second lecture of the lecture series on pericyclic reactions. As earlier I have said in my video that pericyclic reaction incorporates several kinds of reactions by name: cycloaddition reactions, electrocyclic reactions, sigmatropic reactions, group transfer reactions, and cheletropic reactions. All those fall in the category of pericyclic reactions, as pericyclic reactions are the cyclic redistribution of bonding electrons through a concerted process. I mean, that doesn't involve the intermediates. We know that thing. And I have said in my earlier videos as well. So here, as I have focused on cycloaddition reaction in the beginning and more of the Diels-Alder of that kind. So this was the similar slide that was shared in the previous video regarding the types of Diels-Alder reaction that we will cover. So what we are going to do basically in this lecture, we are going to cover more of the regiochemistry of the Diels-Alder reaction to understand more of that, and the product stereochemistry as well. And also we will learn about the synthetic equivalence of some compounds which, when masked, can enhance the reactivity or productivity of Diels-Alder reactions. So in that aspect, this is also very important to understand and to know. And also we will see some of the examples, couple of examples rather say, regarding recent trends and research in these Diels-Alder reactions, and many few I will share in later videos. So as I said before as well, that the types of the Diels-Alder reactions, usually three kinds: the normal 4+2 kind of Diels-Alder reactions, where the diene is supposed to be the electron rich and dienophile is electron poor, the traditional Diels-Alder reaction. Another kind which involves the inverse electron demand, also 4+2 cycloaddition reaction. This, in that case, as by name you can understand that diene should be the electron poor part and the dienophile will be the electron rich one. Hetero 4+2 Diels-Alder reaction will involve a heteroatom as a part of the diene or dienophile, or in both cases of diene and dienophile, heteroatom can be there. Okay, so this will be termed as the hetero Diels-Alder reactions. Now, to solve the problems or to assign the products in terms of regiochemistry and in terms of their stereochemistry, few things, especially the 5 things you need to remember when you assign the product of a Diels-Alder reaction. First, what you need to do, you have to locate the diene and the dienophile from a given substrate. First, you have to locate that, and the characteristic of diene I have already mentioned in my first lecture, so you can go there, you can recollect from there on. And secondly, you have to consider the bottom phase approach for the dienophile. That is another important thing. I will come with the example regarding the exo-endo products, so you will see that in that case as well. Another one, that you have to look for the stereochemistry of the diene substituents in the product. Okay, so the diene can be monosubstituted or disubstituted, and several constitutional diene can be there in terms of position of the substituent in the diene, and therefore you have to look for the stereochemistry of the substituents in the products as well. That is very important. As I mentioned, that the outside substituents and inside substituents, what should be their stereochemistry. Another point that you need to look is the stereochemistry of the dienophile substituent, and depending on that you can have the exo or endo assignment in the product. Okay, so in that case this is also important from the dienophile perspective to assign the endo or exo product. Another one, very important one, is the regioselectivity if both the diene and dienophile are unsymmetrical. I will discuss about that one later on. Okay, so these are points that need to be memorized or that need to be found when you try to solve a problem of Diels-Alder reaction or assign the product structures. So as I said before, that the regioselectivity in Diels-Alder reaction, it two cases can arise. We know that. I have shared in the previous lecture as well, but here I have picked another example here as well, just to say that when non-symmetrical dienes react with the non-symmetrical dienophiles, two situation can arise and two regioisomers in fact are possible, as you can see here in case of case 1 and case 2. In case 1 you see, let me highlight this one so it will be easier for you to understand. So in case 1 you see the one substituted diene gives the ortho product, not the meta one. Okay, now here I should say that if this not be the methoxy group and instead it should be a methyl, that I could not have said that one substitution, then it would have been by virtue of IUPAC nomenclature process, it would have been a 4 substituted diene. Okay, but bear with me in this case that we consider with methoxy substituent here, so we consider this as one substituted diene. Okay, and this is a monosubstituted dienophile as well. Okay, vinyl acetate. So in that case, 1,2 product, that is the 1,2 substituted cyclohexene, that is the major product, and the 1,3 substituted product is found as the byproduct. Similarly, in case of case 2, when the diene is substituted at 2 position, the para product, this is substituted at 2 position if you go through this way, and then the para product, that is the 1,4 substitution in the cyclohexene, will be the major one, instead the 1,3 product. Okay, so we can conclude that this 1,3 or meta product is disfavored in both the cases when we were talking about the non-symmetrical diene and non-symmetrical dienophile. Therefore, when the only they give in both the cases 1,2 or 1,4 product as the major one, and 1,3 products, the meta products, are only the minor byproducts. Okay, so we need to realize the regiochemistry or the direction of Diels-Alder reaction in such cases. Now if we move further and we see another examples that what when we have an unsymmetrical diene regarding with unsymmetrical dienophile. 4 possible options are there, as you can see with case 1 and case 2. In each cases, case 1, case 2 and case 3, in these 3 cases either one of the diene and dienophile are unsymmetrical. For example, in case 1 you see that in that case both of them in that case both of them are symmetrical, the diene and dienophile, so there is no trouble assigning the product structure. And in case of symmetrical, second case, symmetrical diene and unsymmetrical dienophile, that means this dienophile is unsymmetrical, however the diene is symmetrical, there is no problem assigning the product. Whatever way you can arrange that one, it's going to end up with one product only. When we try with the unsymmetrical diene and dienophile is symmetrical, again there is no issue with the stereochemistry or regiochemistry in the product, because only one product is formed. But what about the unsymmetrical diene and unsymmetrical dienophile? What should be in that case? So from here on, with this example, we can also understand that only possible way is to have the 1,2 and 1,4 option if we are talking about the mono substitution in the diene. Okay, so only 2 possible connectivities as possible. I mean, now in that case, in that example, 2 different ways of the diene and dienophile can line up, and the diene and dienophile can come together in 2 ways. For example, first it can be the head-to-head, and in such cases the methyl group of the diene and the carbonyl bond point in the of the dienophile should be in the same direction, giving the top product that we have in the 1,2 substitution product, and they can come together by means of head-to-tail relationship, and in such cases that they point in the opposite direction both the substituents and giving the bottom product. That means in that cases they can give, I was talking about the methyl group and the carbonyl point bond point, they will be opposite to each other, In that case, they will end up with this bottom product. Okay, now since these two have the molecular formula same but different in connectivity, so this will be mentioned as the constitutional isomers. And the big question that comes to our mind, that in this kind of Diels-Alder reaction, are these products formed in roughly equal ratios, or any preference is there? Okay, so the very brief answer if I give, that should be yes. In the Diels-Alder reaction, definitely there has a preference for specific one type of connectivity. Okay, and that means, that signifies that the reaction of Diels-Alder reaction is truly a regioselective reaction. Okay, so next I will talk about some approaches with different examples. For example, here we have the 1,4 disubstituted diene and a electron withdrawing group or substituent containing dienophile. Now in that case, the probable product, according to our understanding in the previous video and here as well, in terms of the substituents of the diene, whether they are in the outside or whether they are inside, in that case, that the outside substituents will be below the plane connectivity. So here you can find out this methyl group here as below the plane here, and this hydrogen atom in the below the plane over here. So the other inside substituent should be above the plane, and that shows over here. And the methyl groups that comes, as I said, from the bottom phase, so it has to go in the below the plane. The carboxylate group will go below the plane. The ester CO2Me group will go below the plane. So this could be the probable product. However, if we consider this one, definitely it along with this one, this will give the same 1,2 product, where both the substituents will go below the plane in the similar kind of stereochemistry. However, we will not get any 1,3 product, right? So we understand that 1,2 and product relationship in terms of the substituents in diene and dienophile will be the major product. Let's see another example. We here have the Danishevsky's diene and we have the vinyl ester, and here we can see that the product is supposed to be the upper one, and here if we rotate in another way of approaching of the dienophile towards the diene, we will not get the 1,3 substituted product or the meta product as the major one. Rather, that can be minor, and in that case that will not form. Okay, so here next I will talk about the endo-exo product formations. First example comes with a symmetrical diene and the dienophile, which is also symmetrical here. And here two possible options are there. I will show that how endo products or endo geometry, I have said in my previous video as well, that preferred over the exo one. So here in that concept we can have, in the first one you can see this should be the endo product, and it can be written as follows in this way as well. This is only the mode of representation in terms to assign these two hydrogen atoms and their stereochemistry over here. So in that sense this is assigned, and definitely these two bonds of this one and this one of this dienophile thing, that will go below the plane obviously. So this should be the stereochemistry of the final product of this diene and dienophile reaction. We will not have the exo product here. Okay, so we can see another example where we have a substitution in the diene and we have a bit substitution in the dienophile as well. So in that case two possible options are there, as I said. However, again in that case the endo product will be favored, as you can see over here, not the exo one. Okay, so in the Diels-Alder reaction the dienophile need to approach from the bottom side to give the major product. So here we will learn about some synthetic equivalence of substrates like the diene and dienophile in the Diels-Alder reaction, especially the dienophiles, and the points that need to be in mind is the synthetic utility of the Diels-Alder reaction can be enhanced by the use of the masked functionality. Okay, here comes the synthetic equivalence term. And as another point, that as ketenes cannot be used as such in the Diels-Alder reaction, this ketene equivalence with masked functionality provide an alternative choice to proceed for the Diels-Alder reaction. So this is the beauty of the Diels-Alder reaction, of masking your dienophiles or substrates. If these are too reactive to go for the Diels-Alder reaction, you can take the masked functionality, and it will provide you an alternative choice to go for the Diels-Alder reaction. And more commonly, that the ketene equivalents are the synthetic equivalents for ketenes are alpha chloroacrylonitrile and nitroethylene. I will show you. So I can show you the structures of these two, the alpha chloroacrylonitrile and the nitroethylene. So in next couple of slides, we will see that how these the dienophiles can be used instead of using the ketenes. So as a substitute of ketene, these can be used, the acrylonitrile and the nitroethylene. For example, here first you can see the cyclohexenone, bicyclic cyclohexenone compound. So if we go for the retro reaction, you can have this diene, cyclopentadiene, and this ketene molecule. Now this can be two synthetic equivalent of this ketene, particular ketene, because they are not that stable. So instead of that, you can use this nitroethylene or this acrylonitrile, alpha chloroacrylonitrile compounds. Okay, so this can be the masked substrate. And how that can be used, for example, if we are talking about the nitroethylene, so this can be the reaction pathway. In the NEF reaction, finally you can have the cyclization, and from NO2 group you can have this product of bicyclic or bridged cyclohexenone compound. And if you use the alpha chloroacrylonitrile, then you have to go for the process like this, and eventually you end up with the potassium hydroxide diamine reaction to give the bicyclic cyclohexenone compound. So these are two possible mode of reactions using the nitroethylene and alpha chloroacrylonitrile compound to get a particular cyclic conformer or cyclic product. There are other examples as well, as I can show over here, that the commonly employed ethylene equivalent in most of the cases can be the vinyl sulfone. Here you can see this is the vinyl sulfone. So this can be used as the masking agent for the ethylene equivalent. For example, here, so how it can give the product, like here you can have the diene system, and you take the vinyl sulfone, you will have the SO2 pH group over here, which can be reduced in presence of sodium mercury, and eventually end up with cyclohexene, substituted cyclohexene compound. So instead of having the ethylene molecule, which is difficult to handle itself, you can have a more easy to control or more easy to handle reagent in terms of vinyl sulfone, and then you can perform the desired Diels-Alder reaction. So this is the importance of synthetic equivalence. It gives you an advantage where the dienophiles which are not that stable or more reactive, and to perform the control reaction you can have some synthetic equivalents instead. Here for acetylene equivalent, vinyl sulfoxide can be used, and you can see here that if this diene system, bicyclic diene system, need to be obtained, and if you retro that thing, you will get this diene and this alkyne or acetylene. Now this acetylene is difficult to use in the reaction, and they are not stable. So therefore, for that you can use the vinyl sulfoxide, which is a stable synthetic equivalent of the acetylene moiety, and then you can perform the reaction with the desired diene system eventually, and upon heating or only you can have this bicyclic diene system as your product. So I hope you can understand how this masking or synthetic equivalents or equivalent substrates are very important for this Diels-Alder reaction to perform any kind of substrates, or any kind of reactions rather, say, where the substrates may be highly reactive or highly unstable. Okay, so in that cases, the synthetic equivalence can be used. Another one is for the alene equivalent, because the synthetic equivalence necessity comes only when you have a dienophile which are not that much stable, and or they are very highly reactive. So in that case you need to have some masking. Okay, so here also alene is quite a reactive substrate or unit. So in that case you also need to have some masking things, and it can be done by the vinyl phosphonium salt, and eventually that can give you the desired product. As you can see over here, this desired product can be obtained with this diene, which is stable instead, and instead of this alene you can use the vinyl phosphonium salt, and then by means of base and formaldehyde you can replace these things by the terminal olefin thing which you have in the product. So you can get your desired product by easy controllable reaction sequences using the synthetic equivalence in Diels-Alder reaction. Okay, so here I'm at the end of today's lecture, and as I said that I will share some recent research and the trends regarding the Diels-Alder reactions. Three examples to mention today. Like you can see with the arine, if you have substituents or some other groups over here. Otherwise you can also term this, if this is like this, benzene, and with this you can as you can see, you can have different auxiliaries here you can attach with, and the functional acyclic dienes, where you have the privilege of putting different substituents, alkyl, aryl, and with the chiral auxiliaries, other functional groups at the terminal positions. That is in order to design any chemical molecule of significance. Okay, like here you can see the people have done the cis substituted dihydronaphthalene building blocks here by means of this strategy, using the arine as a synthetic equivalent of the dienophiles, and you have a separate diene which are pre-functionalized to give your desired product with desired stereochemistry. Okay, so this can be found, and again another example, that with the bromoacrolein derivative and furan in presence of metal catalyst, that will end up with the chiral 7 oxobicycloheptene derivatives. So these are very recent use. Also vinylic furans have been used as the diene system, as you can see here. So this part can be used as the diene system, and with DMAD you can dimethyl acetylene dicarboxylate. If you look at this part, and this was actually a triple bond, so dimethyl acetylene dicarboxylate, this provides you the dienophile, and you can use this vinylic furans at the diene, and by ultrasonic irradiation only you can get the functionalized oxobicyclic alkenes, which are important in sense of their biological activity. And further you have two functional groups, ester functional groups, which can be modified into other functional groups as well, and you can prepare or assign or design any other organic functional molecules which can be of great use in terms of biological aspect or in terms of material science. So these are few examples which are recently reported in terms of the Diels-Alder reaction applications, where you can synthesize different molecules and put substituents according to your desired geometry, stereochemistry, and you can pursue that by means of Diels-Alder reaction. So I hope I have been able to make you understand regarding the regiochemistry and stereochemistry and the synthetic equivalence, the importance of synthetic equivalence in Diels-Alder reaction. Okay, so thank you for watching TG Chemistry. Keep watching TG Chemistry, and don't forget to subscribe my channel and press the bell icon to get the notification further when I upload the videos. Thank you.